Just let me know when I can start.
You are good to go.
Cool. Hi, everyone. I'm Matthew Jagelski. I'm doing the lightning talk version of cryptanalytic extraction of neural network models. This is joint work with Nicholas Carlini and Ilya Mironov. And Nicholas gave the 25-minute version of the talk and made all the slides, so he deserves all the credit for that. The main object of interest for this talk is going to be an adversary with black box access to a neural network model. So a neural network consists of two pieces, the weights and the architecture. The architecture tells you how to use the weights to compute the function. And then the adversary with black box access, of course, means that they can choose inputs to the neural network and they will receive the corresponding outputs. This is a really common setup in practice. So the way that this happens is a company will build a machine learning model, and then they'll deploy it and allow clients to pay to query it. And these models can be really expensive to train. So OpenAI recently released a model called GPT-3, which costs $10 million per training run just to train. And so an adversary has significant financial incentive to try to steal this model because they might not want to write that $10 million check. And so what we're interested in is the power of this adversary who has query access and potentially also access to the architecture at stealing the weights of the neural network. So the existing literature has taken kind of two different approaches to this problem. The first and the most common is a machine learning approach, right? So a very key focus of machine learning is to learn the relationship between inputs and outputs. And so one thing you can do for this extraction is you can query the model 1,000 times, and now you have 1,000 input-output pairs, and then you can use machine learning to try to approximate the function that the black box computes. The other approach, and the one that we take, is a direct analysis approach. So by understanding the mathematical representation of the function, you can use it to reverse engineer the weights corresponding to the neural network's black box. And so our key question is whether with query access to this neural network, we can extract the hidden parameters of the model. And what we find is actually that yes, you can, although there are several caveats that I can't get into. And this is how we do it with these beautiful animations that Nicholas made and actually explains in the 25-minute version of the talk. So you should go check that out. But what I do have time to explain is results. So you can see here, we have a 100,000 parameter neural network model. Prior work is able to query this 1 million times, and they get every weight with 2 or more bits of precision. And we show how to do twice as many queries, so 2 million queries, and we get 29 or more bits of precision. And we have better results for deeper networks as well. So there are 3 main takeaways that we want you to have from this. The first is that neural networks are very commonly analyzed in either like a black box or even an anthropomorphic way. But our work shows that direct mathematical analysis as a mathematical function can be a fruitful approach as well. The second is that secure inference, which is the secure multi-party computation approach to generating this black box query interface, is only as secure as the query interface is itself. So if an adversary can steal the model by making queries, it doesn't matter how secure the protocol for computing those queries is, because the interface will leak knowledge of the model. And finally, it's common in cryptography to model specific algorithms like AES as instantiations of some ideal functionality, like an ideal block cipher. And it might be tempting to use neural networks to do such a thing. But our paper kind of shows that there are subtle properties of neural networks that maybe you should have caution about applying in this way. And so that's it. And I think all of us are here to take questions now.
So there is a question by Kevin. What do you think are the most important open questions area of reverse engineering neural networks models by Kevin?
Sure. So I mean, one of the big ones is like, how do you defend against this? I think there's a lot of different approaches, and it's not really clear which one is the best so far. And of course, like also improving on these kinds of attacks is really interesting as well, because like I said, there are several caveats to our approach that make it not really work in practice. If the other authors have more comments on that.
This is Ilya, and I would add to that a theoretical understanding of the learnability of neural networks. So that's an open question that has been partially addressed in some prior work. We provide empirical evidence that they are learnable, but just understanding the theory of that interface, of that functionality, is still open.
And there's a question. There are two questions in the Zoom chat. The first is by John. Can you comment on the last bullet on this slide? I was not sure what you meant.
Yeah, Nicholas or Ilya is probably best for that one.
Ilya, if you want to go again, you're the cryptographer.
I think, okay, so we want to put in ideal functionalities something that we understand and the parties agree on the implications of executing these functionalities. Like the millionaire's problem, like AX larger than Y, like compare X and Y, or AES circuit, like we understand what executing AES circuit is. With neural networks, they're complex, they're subtle, and it's just asking people to take on faith that executing ideal functionality, like a neural network as an ideal functionality, that is washing our hands of the hard problem.
Okay.
Then Christina asks, if you don't give up confidence levels, does it block the attack?
At least this attack. So the learning approach, you know, that'll work maybe a little bit worse, because I mean, machine learning learns from labels as well as it learns from confidence. This attack, we don't know how to do it for confidence, at least yet. But you know, who knows? In the next couple of years, maybe someone will come up with a way to do that.
Okay, there's more and more questions coming in. So John, tell me when I should stop. I think Moti made more of a comment saying there's actually nothing ideal about them because there's no claim of security. So like, I guess Moti's also following up on the ideal functionality part. But let me move on to questions from Zulip. Have you tried your technique against GPT-3? And how complex is it compared to retraining?
Yeah, that's a good question. So like, the only experiments we have are on these fairly small neural networks, and we actually require a lot of assumptions that wouldn't really hold for like GPT-3 querying. And yeah, I guess the concrete requirement is we need something like 6 or more queries per parameter. And so like these really big models, we would need, you know, 6 times as many parameters as there are queries, which could very well get big.
Eleanor is asking if the attack also can learn something about the data that was used to train the neural network.
Yeah, so I mean, this is something of an orthogonal question, like how. So, I guess like there are black box attacks that you can use to understand the privacy leakage of models. There's also white box attacks. So if white box attacks are better than black box attacks, then extracting the neural network is one way of doing better at that. Although, you know, this is orthogonal to the question of, you know, you can train to make your model more private and whatnot.
So I think I think the time is maybe up. We should probably move on to the next talk.
Yeah, check out Zulip though. There's more questions for you guys.
Thank you. I'm trying to exit.
Okay, do you see my screen?
Yes.
Okay, shall I go on?
Yeah, you got a thumbs up.
Okay, good. Thank you for watching. I'm Emmanuel Thomé, and our paper is joint work with a collection of 6 authors who are listed here. We are reporting on 3 computational records, 2 related to integer factoring and 1 related to the computation of discrete logs. And one of the pretty new things that we have in this computation is that for the first time we are doing 2 records, one for factoring and one for discrete logs at the same time for the same size, which gives a nice comparison point. So we show that cryptanalysis for these sizes is feasible. And believe it or not, you can still see products around that are implicitly relying on the fact that cryptanalysis is not feasible because these products are outdated. So this serves as a gentle reminder that it's very much time to move on. So to do these records, we used a number field sieve algorithm, which is a complicated algorithm. And most of what I'm going to talk about in this 5 minutes is related to the 2 most computationally expensive tasks, which are sieving and linear algebra. So for sieving or relation collection, there's a difficult art, which is the art of choosing parameters. And we were pretty proud that our parameter choice was really good for these computations. And we combined several techniques. Many of them were known already, but have seldom been used for records. Specifically, I'm thinking of what we call composite special queues, and also batch smoothness detection, both of which played an important role in the computation. Most of this was aimed at making the linear algebra computation that came next easier, and all of these choices were guided by simulation tools that we used in order to decide which parameters were relevant and how we should tune them. Regarding linear algebra, so here are the dimensions of the matrices that we encountered. These are large, sparse matrices. And the matrix for the DLP problem is much smaller because the DLP linear system is defined over a large finite field. So much of our effort was aiming at reducing this linear algebra dimension so that the task was feasible. What we show in our computation is that linear algebra at these sizes does scale. And this is thanks to the use of the block-Wiedemann algorithm, and also thanks to the fact that we have an improved implementation of what we call the generator step, which is the bottleneck step in the block-Wiedemann algorithm. If I draw a picture with the time to solution with respect to the number of cores I'm using, if I have something completely perfect in terms of scaling, I have a straight line. And what we have in this context is approaching a straight line, at least until several thousands of cores. So this is something we are pretty happy with. If we do the total of the cost of the computation, we have for RSA 240 something which is in the whereabouts of 900 core years, and for GLP 240 something that is slightly above 3000 core years. So this tells us that we have a hardness ratio which is 3 point something, which is significant, but on the other hand, it is not as large as people tend to think. So it's something that we learn from this computation. Also, we can make the comparison of our computation, namely the DLP 240 computation, with the latest record of this kind, which was DLP 768, which is 232 digits, and that was 4 years ago. And what we found out is that on identical hardware, our harder computation would have taken less time. So this is something we're also quite satisfied with. At the conclusion, more than just record, we have developed parameterization strategies for further computations, which were pretty effective in these instances. And those were guided by the design of a simulation framework, which we found pretty efficient. It's not perfect, but we were quite happy with it. Our implementation scales were, and also it's important to notice that we used open source software, CADO NFS, which we have been developing for more than 10 years in Nancy. And also all the parameters and some data to reproduce part of a computation can be found under this internet URL. We intend to go on with larger projects, and most of the focus will be on our capacity to anticipate the hardness of the different steps and our capacity to use a large amount of computing power. Okay, thank you for listening, and I'm here to take your questions.
Okay, first, Emmanuel, sorry for not introducing you properly. I'm learning on the job. I don't see any questions yet, but I have one.
Okay.
So my question is, how stable is this? In terms of like you made some progress, and then like do you feel like it's saturating and we kind of have a good idea of like how much this actually costs, or kind of do you expect there will be significant progress in speeding this up going forward?
Well, we can always expect some progress based on the fact that we improve on the implementation and so on and so forth. But what we found out is that I mean, the different choices that we made in choosing the parameters ended up in costs that were pretty stable. I mean, at the end of the day, we were talking a few % difference between that parameter choice and that other parameter choice. So in a way, yes, it's as stable as it can be. Well, of course, if tomorrow somebody comes up with a totally new algorithm, it's going to be different. But
Kevin asks, do new processor architectures like GPUs help for sieving?
Nope. I mean, we tried, but I mean, the people at EPFL tried to use GPUs, and the bottom line is that if you have them in large quantities, maybe you could use them to some extent. But if you have money to spend, you're much better off spending it on normal CPUs. That's far.
And Habib asks, can you comment on what the strategies for choosing parameters are exactly?
Difficult. I mean, it's a question of making sure that you give enough legroom to the filtering process to reduce your matrix size as much as you can. So it means that we want to pay attention, for example, to the fact that the special queues that we use to divide the work into pieces do not actually cover a large part of the large prime range and do not interact badly with the filtering that comes next. This is one of the key aspects, and this is detailed in the paper.
I don't see any more questions for now.
I guess if there are no other, if there are no other questions, I was going to say we can go on to the next talk. Did you want to say something?
No.
Okay, so does the next speaker want to load up her slides? Share her screen? Okay, so.
Okay, can you see slides and sound?
I don't see any slides right now, actually.
Oh, okay.
I saw them a minute ago, but not right now. Oh, there we go. There we go.
Okay, I need to enter the full screen mode though, and that's when you lost the slides.
Yeah.
Oh, I'll just share my desktop instead of the thing. I think yesterday they had a similar issue, so. Let me just stop sharing for a while. Okay. Is that better?
Yeah.
Okay.
The next talk will be on discrete logarithm algorithms and pairing relevant finite fields by Gabriela Di Michele, Pierre Gaudry, and Cécile Perrault. And apologies for the names if I got any of them wrong.
Thanks for the introduction. So as you just said, this is a talk, joint work with Pierre Gaudry, Cécile Perrault, and I'm going to be talking about discrete logarithm algorithms and pairing relevant finite fields. So let me just start by briefly recalling the discrete logarithm problem. So the definition is quite straightforward. We're given a cyclic finite group G. We have a generator small g from this group, and then we have a target element H of this group. And we want to be able to find the exponent X such that if I raise the generator G to the X, then I end up with my target element H. So this is one of the two main mathematical problems on which the security of a lot of today deployed protocols base their security on. So the other one being factorization. And in this work, we were motivated by an interesting example that uses the hardest of DLP, which is pairing-based protocols. So why do we really care about pairing-based protocols? Well, first of all, they've been used. There's quite a lot of protocols, old ones more recently in blockchain, for example, ZK snarks. And what is interesting with pairings when looking at the hardness of DLP is that we want to have the hardness of DLP both on elliptic curves and on finite fields. So these pairings that I'm not really defining are bilinear maps from a product of groups to a target group. And so in order for a pairing to be secure, we want the discrete logarithm to be hard. And this comes from the definition of the group G that we have. So here in this work, we try to explain and ask the question, so how do we construct a secure pairing-based protocol? And the answer, which is simple but not simple, is to look at DLP algorithms on both sides. So I'm not really going to talk about the elliptic curve side. The complexity is the square root of the size of the subgroup that's being considered, and that comes from the polar row algorithm. But on the other hand, I'm going to be talking about the discrete logarithm on finite fields. So this is a bit more complex. First of all, there's a lot of different algorithms that solve DLP on finite fields of the form FPN. And not only there are a lot of them, but also their complexity is going to depend on a relation we have between the characteristic P and the extension degree N. So usually when we talk about complexities of these algorithms and also these finite fields, we have this L notation, which is the formula on in the green rectangle. And this is used to express the complexities of these algorithms, but also to define different families of finite fields. So we usually talk about small, medium, or large characteristic, depending on this L notation, where depending on whether the LP, which is the first of the two parameters in the definition, is smaller or equal or greater than a third or 2/3, we're in either of these families. So we're going to focus on a specific area, which is the boundary case between small and medium characteristics. And there's two main reasons why we focus on this area. First of all, it hasn't been studied before. So we have a lot of algorithms in a medium characteristic, and we know their complexity, how they behave. There's been a lot of work on small characteristics, especially in the recent years with the whole quasi-polynomial time algorithms. But specifically at this boundary case, there's a lot of algorithms that coexist. And we were interested in studying their complexities precisely there to see which one performs best. And the other reason why we focus on this area is because this is the area where pairing stakes their values. And so this was our motivation. So the main results of our paper, obviously all the details are in the longer talk or in the actual paper, are a thorough analysis of the behaviors of many algorithms, which I haven't even mentioned yet, in this specific boundary case, at the specific boundary case. And this analysis allows us to estimate the security of pairing-based protocols. So in the end, this is kind of the summary of our results for the first question. So the algorithms that we study are the number-filled sieve, which was mentioned in the previous talk, and all of its variants. So there's a lot of variants that has been developed in the past years. I mean, some quite older. We have the multiple number-filled sieve, the tower number-filled sieve, the special number-filled sieve. And then if you look at the plot, there's some letters that come after the name of the algorithm. This is the polynomial selection that is used to select the two polynomials at the beginning of the algorithm, and this influences the complexity. So there was a lot of studying to do here, and this are the resulting complexities that we have. So there were some surprising facts that we noticed. For example, the special tower number-filled sieve, so if we're combining two variants, was not an algorithm that is applicable in this specific case because the complexity was much higher than any other algorithm. So in the end, we had kind of an overview of what happens at this boundary case. So we have the function field sieve, which is another algorithm similar to NFS, except we're using function fields instead of number fields, which is still the best algorithm for in the left area and for kind of for small CPs. And then at some point we have crossover points, which we define precisely in the paper. and all the variants of NFS, depending on the considerations you're making on P and N, that kind of fight to be the best at this boundary case. And if we fall into small and medium characteristics, then these were known results. So in the end, after we've done all this analysis, we were actually aiming to answer the following questions. So asymptotically, what finite field FPN should be considered if we want to achieve the highest level of security when constructing a pairing? So basically, we want to be able to say, okay, if you take this P and this N, then you're achieving the highest level of security. And we did that by equating the complexity on both sides. We want the discrete logarithm problem to be as hard on the elliptic curve side and on the discrete the finite field side. And so we were able to, once we've computed, all the complexities in the plot in the few slides above, we were able to determine these intersection points. And for, again, whether you're choosing an N prime, an N composite, or a P of a special form, etc., define which were the intersection points, so the CP and the L notation and the corresponding complexity for the best optimal finite field. And again, there were some surprising facts that we noticed. For example, if we use a special form of P, which allows us to use the special number field sieve algorithm, then we're not always necessarily making the pairing less secure, which was a surprising fact that we noticed. All the details are in the paper, and thanks for listening.
Thanks. So questions not yet on the chat, but I have one. So the parameter selection is right at the boundary between small and medium. Does it make you nervous? Or should we be nervous about this being right at this boundary?
Nervous in the sense that some ideas from the small characteristic could be applied to improve algorithms. Yeah, that's one thing that we hoped for. And I don't think nervous, exciting. It's but yeah, I mean, it's right at this boundary point where we have very different algorithms that share some similar ideas, but use some different techniques. So yeah, no, I think it's interesting whether to understand whether some of the quasi-polynomial stuff can be used at this boundary point. But so far we haven't. They kind of blow at the boundary point. They're not the optimal algorithms in this precise area.
Okay, sorry, I forgot I was in the Cryptanalysis session, so we're excited about breaking stuff here.
Yeah, we are.
And then John asked if there's a lower upper bound for discrete log complexity as a function of P and N, say when N is prime.
Wait, I didn't hear the question. A lower bound?
Is there a lower or upper bound?
Just a simple, I mean, I'm looking for just a simple expression. I mean, you know, if you want to summarize what the results say.
If I want to summarize, these would be upper bounds. I think the values we give is for rho equals 1 when considering elliptic curves. So these would be upper bounds, because then the complexity, I mean, I think I have an extra, wait. The following slide, I think may answer your question. I'm not sure I understood, but the complexities decrease when CP increases. So the values we give, which are the intersection points, would be upper bounds for I mean,
these, I think I was looking for, I didn't quite understand this graph because I was expecting some kind of a graph with like P on one axis and N on the other, and then the complexity plotted as a function of P and N.
Oh, so the complexities of these algorithms are usually expressed with this L notation that I introduced in the very beginning, where it's L of one.
But that only depended on P to the N. It didn't depend on P and N separately, I thought.
Yeah, it depends on, yeah, a relation. You have a relation between P and N. Maybe I'm not understanding quite well.
So go back to that slide.
Sorry, which one?
Back at the beginning, the one with the expression that you had. Yeah, yeah, that's one, right. So this only depends on P to the N. It doesn't depend on P and N separately. So the point is that that C, I guess, depends on P and N separately, right?
So no, the complexity of your algorithm. Oh, you mean on P and N? So we're looking at. I'm not sure I'm going to answer this quite correctly, but my co-authors are also there if they want to add something. The complexities of these algorithms, we looked at them asymptotically, where P and N kind of go to infinity, following the relations that link them throughout this L notation. So here we look at the binary case where P equals L cubed 1/3 of CP, which gives a family of finite fields and a link between N and P. And when these tend to infinity, then asymptotically, we look at these complexities.
Okay.
So there were more questions on the chat. Kevin asks, how safe is it to extrapolate these into the future, given that CPUs are improving? He wrote similar paper 25 years ago, but his phone is now more powerful than the supercomputer he used back then.
So the question is, how safe is it to extrapolate these results?
Yes, into the future, given the advances in CPU architectures.
So complementary to this work, there's some papers that look at actual parameters for pairing-friendly curves. And there's a mismatch between some of the results that are observed for lower security levels and asymptotically, the behavior that's happening asymptotically. So I don't really know if these results, I mean, I think there's a need for more analysis for these algorithms, especially with growing finite field sizes, and also other algorithms. So we just have an implementation of NFS, and we could have an implementation of some of the variants of these algorithms to see how they behave in practice.
So probably we should go on to the next speaker, I think, at this point.
Okay, Gabriele, do check the Zoom chat though, because there's more questions for you.
I will check it.
Okay, so the next talk is going to be given by Agnes. So can you share your screen? Okay, this is Agnes is presenting joint work with Jean-Sébastien Courant on a polynomial time algorithm for solving the hidden subset sum problem. Thank you.
Okay, hi everybody. As you said, my name is Agnese and I will present you our polynomial time algorithm for solving the hidden subset sum problem. This is a joint work with Jean-Sébastien Courant. Well, we want to solve the hidden subset sum problem, so it's good to define the problem first. In the hidden subset sum problem, we consider an integer q and n random integers alpha 1, alpha n, which are defined mod q. In addition, we consider n binary vectors x1, xn of length m, and a vector h, which is a combination of these binary vectors with these weights alpha i's, mod q. You can read the relation in this slide. Then the problem is given the modulus q and the samples vector h to recover both the integers alpha i's and the binary vectors xi's. It's also convenient to write this relation using vectors and matrices, like in the bottom of this slide, and then X is a binary matrix whose rows are the xi's, the binary vectors. But why hidden subset sum problem? Well, you can notice that actually each component of the samples vector H is actually a subset sum respect to the weights alpha i's. One in the classic subset sum problem has to recover only the binary coefficient, but in this case, the weights are hidden too. And for this reason, actually, the classic attacks for the subset sum are not applicable in this case. Before speaking about the algorithm, I just want to speak about briefly the history of this problem, which was presented for the first time at Eurogroup 98 in the context of the generation of random DLP pairs. The following year, Nguyen and Ster described a lattice-based algorithm for solving this problem. Well, the fact is that despite for small n, this algorithm is quite efficient. At the time, they were not capable to break the problem for n greater than 90. So in our paper, we provided a detailed analysis of the Nguyen-Stern algorithm, explaining this practical behavior. And we found the bottleneck of the algorithm and solved it, providing a variant which works in polynomial time. In this slide, you can see a sketch of the structure of the Nguyen-Stern attack. Remember that as input, we have H and Q, and we want to recover the binary matrix X and the vector of the weights alpha. And at the top, you have the relation holding. The Nguyen-Stern attack actually is divided into main steps, and also our algorithm has the same overall structure. We decided to maintain this structure, and I will explain you why in the next slide. Indeed, analyzing the Nguyen-Stern attack, we observed that actually the first step succeeds with good probability in polynomial time when the modulus is large enough. Instead, the second step is the bottleneck of their algorithm. And the reason is that in the Nguyen-Stern attack, they use a lattice reduction algorithm to compute the binary vectors as short vectors. But we observed that these are actually shortest vector of the algorithm. And for this reason, the asymptotic time complexity of the attack cannot be polynomial time. So in our paper, we decided to have a new second step, completely different, using a different approach. Our second step is indeed an algorithm to recover binary vectors using a multivariate approach. Namely, we solve a multivariate quadratic polynomial system via linear algebra. And for this, actually, we require a number of samples m, which is quadratic in n. And but in this way, we obtain a polynomial time algorithm. We needed to require more samples, so we also had to improve the first step for generating fast, more orthogonal vectors. I just want to mention that actually we also consider the fine hidden subset sum problem as in the Nguyen-Stern paper of '99, providing an analysis and a variant also for this problem. So summarizing, in our paper, we describe an algorithm for solving the hidden subset sum problem, which works in polynomial time with the same minimal size of the modulus, but we require a number of samples which is quadratic in n instead of linear. And this was confirmed by the practical experiments too. So the main questions left are if we can reduce the minimal size of the modulus log Q, and if we can further reduce the number of samples. Indeed, I mean, would be nice to have a polynomial time algorithm requiring just a linear number of samples. Regarding this question, I just want to mention that in the full version of the paper, we describe two different methods to slightly reduce the number of samples. But for both cases, we still need a quadratic number of samples to achieve a polynomial running time. So that's it. Thank you for your attention. And if you have questions, I'll be happy to answer.
Great, thank you. I see one question on the chat from Alexei. In your paper, the eigenspace exploration technique for pulling out solutions from their span looks generic. Have you seen it somewhere before?
Well, it's actually using these techniques for using linear algebra techniques for solving multivariate quadratic system is something that was already used. There are other works also from the 80s, I think, and this is a bit. I mean, usually this system, this multivariate system use a different language, let's say, And you can find something similar in the Grosvenor basis language. But yes, but yes, we used these. We couldn't find anything that fitted as good as this technique.
And then another.
I'm afraid we're out of time. Sorry.
Oh.
But,
okay. Okay.
I'm just conscious of the fact that there's another session starting after this one. So I have it on good authority that Julian Ross is here. Who's giving the last talk? If that is correct, could you please share your screen and thus your slides?
Balthazar is, I think, giving the talk.
Oh, okay. Then my good authority wasn't correct. Balthazar, can you share your screen? Okay, I propose, John, you ask that outstanding question.
Are you hearing me?
Oh, now I hear you, Balthazar. Yeah.
Okay. Yep.
I don't see. I'm not sure if that's my connection, but your sound is very chopped.
Sorry, there is a little problem. Do you hear me?
Yeah, we can hear you now, but we can't see your screen.
Okay. Oh, I don't know why. Oh, it doesn't work anymore. Sorry. Sorry. I think I have to reload, but it will take few seconds.
Okay.
So maybe if we're waiting, we can go back to the last talk and ask the remaining questions.
Yeah, let's do that.
So the question was, suppose I want to use the HSS optimization to generate many pairs of the form x g to the x. How does your work affect how to do that? I don't know if Agnesi is still on the listening.
Yes, sorry, I was trying to answer a question. Are you speaking with me?
Yes, the question, John was asking the outstanding question why the last speaker is fixing some technical problem.
Oh, sorry, I was trying to answer the question in the chat.
Oh, okay, okay.
This was the question you asked me?
Yeah.
Oh, sorry. Yes, what I was writing now, exactly now, that actually our work implies that one should not generate many pairs using that optimization, because as you reach a quadratic number of pairs, it means that you reach a quadratic number of samples. And
sorry, can I butt in, because I just received a message from Balthazar. He has some problem with the internet. Is any of the co-authors prepared to give his presentation?
Well, I'm on, but I do not have the slides. So I'm asking him if he can send me the slides.
Okay. In the
back.
meantime, Agnese, feel free to continue answering the question. Sorry for interrupting you.
No, it's fine. No, I was just saying, I don't know if I understood correctly the question. If you want to use this optimization to generate these pairs, quadratic number of samples, when I say this during the presentation, I meant that as soon as you produce a quadratic number of pairs, you can be attacked by our algorithm. So yes, one should be careful to reuse the same set multiple times.
Okay, Julian, any update?
You know, I still have not got the slides, so I guess if there is a technical problem, then I can try to give the talk without the slides. I mean,
yeah, it might be safest for you to just freestyle it. So, so this work is about classification of computational assumptions in the algebraic group model. It's by Balthasar Bauer, Georg Fuchsbauer, and Julian Loss, and Julian is going to give the freestyle presentation now. Thanks, Julian.
Yeah, so sorry for the technical problems. So our talk or our paper is about, as you pointed out, a classification about computational assumptions in the algebraic group model. So what do we mean by this? So the algebraic group model, to give some background, was a model that Georg Fuchsbauer, Eike Kilz, and myself proposed in a paper at Crypto 2018. And it basically is a relaxation of the generic group model, and it fits in between the generic group model and the standard model of computation. And in this model, the adversary is limited in the sense that it has to show how it computes new group elements, but it is able to see the actual representation of group elements, whereas in a generic group model, it does not get to see these group elements. Now, there were a lot of papers recently that explored new proofs and relations between different assumptions in this model. For example, you can show that the computational Diffie-Hellman assumption is tightly equivalent to the discrete logarithm assumption in this model. You can also show that practical signature schemes like the BLS signature scheme have a tight reduction to the discrete logarithm problem, even though it is known that because this scheme is unique, it does not have a tight reduction if you just assume the random oracle model. And in this paper, we sort of asked the question, is it possible to give a broad meta theorem that lets us reduce a certain type of assumption to another general type of assumption, okay? And let me make a bit more clear what I mean by this. So basically in our paper, we give general theorems for computational number theoretic assumptions over groups. Let's say they are prime order. We also consider pairing groups. And we make theorems of the following form. So we say that if some condition in the exponent of the generator holds, so if the polynomial which you have to compute as part of solving this number theoretic assumption, if it satisfies a certain condition on the degree, then we provide a generic and tight reduction from the associated discrete logarithm problem, where the adversary gets to see all of the degrees in X. So it would get to see if the degree of this specific number theoretic problem would be Q, then the adversary in this Q D-log assumption would get to see G to the X up to G to the X to the power of Q. And so now we show this generic reduction in our paper for many different types of assumptions. And we also provide a separation result. And the separation result shows that you can actually not only classify these group assumptions, but you can also separate different classes. So one class is strictly stronger than the other with respect to algebraic reductions. And this is sort of the second part of our paper. yeah, I think Balthazar has now just put up the slides. So this is like the second part. So we show that the Q+1 D-log assumption is a strictly easier assumption than the Q D-log assumption. And that means that all of the number theoretic assumptions that can be implied by the Q D-log assumption are strictly strictly stronger than the ones that we can imply by the Q+1 D-log assumption. And then we also have another theorem that shows that there are some assumptions which we cannot capture in a framework, such as the one more discrete logarithm assumption. And that basically sums up the results of my talk. I'm sorry that there were these technical difficulties, but please do check out our paper. It is on ePrint. And yeah, thank you for your attention.
Great, thank you. So if there are any questions? I don't currently see any.
Well, John, you asked a question in the chat.
Yeah, I wanted to know if you can share your slides.
Oh yeah, sure. We can.
No,
do that.
I'm kidding. Actually, I'm kidding.
Okay.
You know, yeah. Actually, if you want them to be here in the permanent video archive, you can go through them more slowly. So at least they'll be there in the background.
I still don't have the slides, so.
No, but Balthazar can do it.
Yeah, can maybe do it. Yeah. So.
I'll just make a comment to all speakers that if you upload your slides to the link that was provided, I will link them from the program after the conference.
Okay, let's do it like that.
Actually, I was going to ask Kevin, the previous ones, none of them are going to be available until after the conference?
I haven't collected them. I'm afraid I had too many other things to do.
Okay, no, that's fine.
Sorry.
Maybe on that note, we should all thank all speakers of this session because we're a little bit over time already. Let's try this thing where we unmute ourselves and give a round of applause and see kind of how that kind of plays out.
Woo!
Okay, thanks everyone.
Thank you, everybody.
Thank you, yeah.
Thank you.
Thanks.